Alright, good morning. So I'm going to be going over the key for circular motion and static forces unit test. So this is so you can check where you went wrong or how to do certain questions if you didn't know how to do them. So what is the tension of the two ropes? So we have two ropes, 42-degree angles of elevation, and this box weighs 212 kilograms. The answer is how much tension do each of these ropes have? Okay. So overall, you want to start with all these questions with kind of the sum of the forces in the x direction is 0. So if we look at the sum of the forces here, that means if we make little triangles here, this is 42 degrees, and then we have another one we can make here that's 42 degrees. And we want to know what this is, which is 42 cos of whatever this is. We'll call this T2, and we'll call this T1. So that's what that is. That is what that is. This is 42 cos T2. Oh, wrong way. T2 cos 42. And this one's T1 cos 42. So if we want the x direction to be the same, that means those two have to be the same. So overall, T1 cos 42 should equal T2 cos 42. Okay? And then overall, you know that those will cancel out. So we know that one of our equations is both of the tensions of the two ropes have to be the same. T1 has to equal T2. Okay, so let's find out what that is. How to do that is now we go the sum of the forces in the y direction must be 0. So if that's to be true, then that means these triangles, these two are going kind of up, so that has to equal the force of gravity going down of this box. So the force of gravity is just 212 times 9.81. And we get 2,079 newtons. So since the thing is not moving, that means the two forces of these ropes upward have to equal this. Okay? And since we know they're going to be the same, it's going to be T2 sine 42 and T1 sine 42. Okay, so we know T1 sine 42 plus the y direction of the other one, T2 sine 42, have to equal this 2,079 newtons. So now since I have that equation, I know that these two things are the same thing. So it's really the same as 2 times, we can just call it tension because we know the tension is going to be the same for them both. Sine 42, two of these things equals 2,079. And then we have to solve for t. So we divide by 2 and we divide by sine 42 and we get t equals 2,079 divided by 2 sine 42, and our overall tension is 1,554 newtons is either of them. So that's 1,554, 1,554 newtons. And that question's done. Okay, let's move on to the next one, a torque question. 60.5 Newton force is exerted at an angle of 40 degrees from parallel. How far must it be to produce a torque of 500 Newton meters? Okay, so we start with our equation. Torque is just F times L sine theta. Okay, so here's our pivot, and it's saying how far from that pivot should it be so that you get 500 Newton meters over here. So let's fill in our equation. 500 Newton meters. Our force is 60.5 newtons. Our length we don't know, and the angle we're pushing at is 40 degrees. So now we just have to solve for L. So we can go 500 divided by 60.5 and divided by that sine 40 as well is equal to our L. So overall our L is 12.9 roughly meters. Has to be 12.9 meters away to get that torque of 500 Newton meters. Alright, so now we're going to go into the next one. The force of gravity on the beam. This beam right here is 1200 newtons, force of gravity. What force must be exerted at A to maintain equilibrium? Because we know if there's no force here, since the center of gravity is beyond either of these two kind of pivots, you can picture this as a diving board, the beam would just fall, right? So if we picture this as our pivot, there has to be some force also down on here to cause it to not rotate, okay? Because if you have your pivot in the middle of the two forces, one here would cause a rotation clockwise, and then this one would cause one counterclockwise, so they would cancel out. So the torques have to be equal. So torque 1 has to equal torque 2. Okay, our torque 1, we'll call it this one, is just F times L. And then our torque 2 is FL. It's the force of the second one and the length of the second one. Okay, so here, our force here, we don't know. And then our length is 2 meters from the pivot. And then our force 2 is 1200. And our length 2 is 1.8 from the pivot. Okay, so overall our force is equal to, it's going to be 600 times 1.8, or 1080 newtons downwards. Has to be down. If it was up, it would actually rotate faster. Okay, on to the next question. The ride the revelation at the peony spins such that it's completely vertical. It's a vertical circle. Yeah, it reaches 100 kilometers per hour. I see that. I got to convert that right away. So let's convert that to 27.7 meters per second. And has a 160 foot arm. I know I got to convert that right away, which is 48.78 meters. And we know this is going to be our radius. One arm is our radius of this ride. What is the highest apparent weight that someone would feel? So I'm picturing myself on this ride, and as I go up, I kind of feel more weightless up here, and then I go down and I feel heavier right at the bottom. Okay, and we know the bottom of a vertical circle is just force of gravity plus the force centripetally is kind of what you feel. Okay, so there are 3.28 feet in 1 meter, so that is helping the conversion here. So if I'm going to solve this, I've got to find out what Fg and what Fc is. Fg is just 9.81 times your mass. Okay, do they tell us your mass? Nope. Fc is equal to your mass times v squared over r. Our v squared is up there. So Fc overall is this mass times your 27.7 squared, and your radius, which is 48.8 meters. So let's do the math for that. And I get 15.8 when I calculate that, m. So our force centripetally is 15.8 kind of acceleration times your mass, and then your force of gravity is 9.81 acceleration times your mass. So there's actually more force centripetally here in this ride. So if we want Fg plus Fc, we write Fg plus Fc is 9.81 m plus 15.8 times your mass, and we end up with 25.6 m. Okay, what does that mean? It's really acceleration times your mass, right? So it means that you're accelerating 25.6 meters meters per second squared. Okay, so if you wanted to write your answer, you would say your acceleration is 25.6 meters per second squared. Or if you want to know how much g's you would feel, you go 25.6 your acceleration divided by 9.81, because that's what a g is. And then you would get 2.6 g's. Okay, so you'd feel 2.6 g's at the bottom, which is 2.6 times heavier. You would feel 2.6 times heavier. You wouldn't be any heavier, but you would feel 2.6 times heavier. All right. Next problem here. The Earth is 1.49 times 10 to the 8 kilometers from the sun. I see kilometers, so I'm going to convert it to meters right away. So that's times 10 to the 11. And here as well, 1.08 times 10 to the 11 for Venus on average. Use Kepler's third law to calculate the length of Venus here in Earth years. So we start with k equals r cubed over t squared. And then this is equal to 1.49 e to the 11 cubed. And we know the period of Earth, because this is the mean radius of Earth, we need to know the period of Earth, which is 365 times 24 hours times 60 minutes times 60 seconds to get the period in seconds squared. Okay, so our k overall is going to be 3.326 e to the 18, just some really big number. Now we're going to do this equation again, but for Venus. Okay, this is the mean cubed over t squared of Venus, which is this number for our k, 3.326 e18. Our r, which is for Venus 1.08 e to the 11 cubed. And then over here it's going to be just t squared, because that's what we're trying to find, or how much of a period is Venus. So we're going to go t equals, we solve for this, it's the square root of 1.08 e to the 11 cubed over 3.326 e to the 18. And then so overall our t is 1.946 times 10 to the 7 seconds for Venus. What does that even mean though? Just a lot of seconds. So we're going to convert it to Earth years. So if we want to convert it to Earth years, we're going to do the opposite here. Divide by 60, divide by 60, divide by 24, divide by 365, and we end up getting 0.62 Earth years. If people put answers as like 225 days or whatever it was, that was right as well. So taking into account both centripetal acceleration on Jupiter and universal gravitation, what would a 75 kilogram person's apparent weight on Jupiter be? Jupiter's mass is this. This was a tough problem. So you got your circle, okay, you're standing on here, and then you have the radius here of Jupiter. And Jupiter's huge. So what you're going to calculate is you're going to calculate your FG, okay? In this case you have to use, because it's a different planet, universal gravitation. Okay, you need to find your force of gravity of this person on Jupiter. So we're going to do this, and this is going to be 6.67 e to the negative 11 times their mass, 75, times the mass of Jupiter, times the radius of Jupiter, squared. Okay, so your FG is 1937.7 newtons. Okay, and if you divide by the mass, you can kind of get the acceleration of the planet as well, which is a side fact, around 25.8 meters per second squared instead of 9.81. So you'd feel really heavy just standing on there. Okay, and it says also take into account centripetal acceleration. Okay, so generally a centripetal acceleration is kind of a force that takes away some of this weight. It kind of makes you want to go out. Okay, so some of this Newton force has to be canceling out that centripetal acceleration that's causing you to go around in a circle as well. So let's just find out what Fc is. That's mass times v squared over r. Okay, actually that one won't work because we don't know what v is. So let's use 4 pi squared r over t squared. Let's use that equation. So it's going to be 75 times 4 pi squared, the radius of Jupiter, over the period in seconds. It says it rotates in 9.8 hours. which is quite a bit faster than Earth's. So 9.8 hours times 60 minutes times 60 seconds squared, and then we end up getting 166.52 newtons. Okay, so that means centripetally you are rotating around in a circle, such that the force holding you in should be 166.52. If there's nothing holding you in there, you would continue tangentially. So that means that force that's keeping you in has to come from somewhere. It has to come from here. Okay, so you have to actually minus it from your force of gravity. So it's Fg minus Fc, which is 1937.7 minus 166.52, which will end up being 1771.18 newtons, and it ends up being 2.4 Gs. Okay, so just standing on Jupiter, you would feel 2.5 times heavier. Alright, now this one here, there was a few people that tried to do Fg equals Fc to begin with. And if you did it that way, I still marked it right, just because it was a different way to interpret it. But all I was looking for this question is you go in a loop. The height is 7 meters, not the radius, but the height. Okay, so here they want to know how fast you have to be going at the bottom so that you make it past the top of the loop there. Okay, so here you go energy at spot 1 as 1, and then we'll say it's 2. Energy at spot 1 has to equal energy at spot 2. That's the potential energy at spot 1 plus the kinetic energy at spot 1 is equal to the potential energy at spot 2 plus the kinetic energy at spot 2. Okay, so potential energy at spot 1 we'll say is at 0 height, so that's gone. Kinetic energy at spot 2 we'll say you just made it over the top. We'll say you make it to 0. So I guess in this instance we're saying that if you make it to the top, somehow you're connected to the railway, so it won't drop. Okay, some people did the Fg equals Fc to see how fast you would have to be going up at the top if you weren't connected to the rail itself, and that was right as well. Okay, they would have got a slightly different answer. Here we'll say that it's connected to the top so that if you reach the spot and you're going 0, it would continue rolling down because it's connected to the rail itself. Okay, so either way would have been correct. P energy at spot 1 is mv squared, and we're trying to find out what that v is. Potential energy at spot 2 is just mgh. Okay, the m's cancel out. So if we're solving for v, it's going to be square root of, well, times by 2 on this side, 2gh. Okay, and this is h at spot 2. Okay, so it's going to be square root of 2, 9.81 times 7 meters. So it's going to be just square root of 2 times 9.81 times 7, and we get 11.72 meters per second is the minimum speed you have to be going at the bottom, not even taking into account friction or anything, to reach the top there. Okay, so in reality you'd have to be going much faster than that. And I would guess somewhere around 20 meters per second. Okay, 8. What is the escape speed of Mars? What does this mean? The mass of Mars is that, the radius is that. So here, escape speed, we know that we have to do this energy equation. Okay, so potential energy at spot 1 plus kinetic energy at spot 1 equals potential energy at spot 2 plus kinetic energy at spot 2. I have my circle here. We're saying the outer is 1 and infinity is spot 2. Okay, so you have to go from spot 1 to spot 2. So potential energy at spot 1 is negative g m1 mass of the planet over r plus the kinetic energy, which is half mv squared. Potential energy at spot 2 is negative g m1 m over r plus half mv squared at spot 2. Okay, we're going to say your speed goes to 0 when you hit spot 2, so that's going to go away. We're going to say that your potential energy is 0, because that's the definition. It says when you go to infinity, your potential energy goes to 0. Okay, that's why I can cross that off. So overall it's negative gm, big M means the mass of the planet, plus half mv squared equals 0. And that's how you do escape speed, is you really make it equal to 0. And you have to find out what v is going to be to get out from 1 to 2. Okay, so let's solve for v. We're going to add this whole expression onto the other side. So we're going to get half mv squared equals g m giant M over r. Solve for v. So we're going to multiply by 2, divide by m. So it's going to be v equals square root. When I divide by m, it's going to cancel out that m. So it's going to be g, the mass of the planet, over r. And then we had multiplied by that 2 as well. So it's square root of 2 gm divided by r. So overall v is square root of 2, 6.67 e to the negative 11. Mass is 6.4 e to the 23. And then our r is 3.4 e to the 6, which gives us 5,011 meters per second to fully escape Mars gravity. And that's what it means, the speed you need to escape Mars gravity field. Okay, so if you go faster than that, you're good to go. Alright, last 2 questions here. If a car rounds a circular corner at 40 meters per second and the radius of the corner is 200 meters, you're going around this radius is 200, and your v is 40 meters per second, and your mass is 500 kilograms. What is the minimum coefficient of friction? So we know there's going to be a centripetal force here. Let's find out what that is. Fc equals mv squared over r. Our mass is 500. Our v is 40 squared, and our r is 200. So our Fc is going to end up being 4,000 newtons. Okay, so we know that there's a force keeping you in the circular path. If that force wasn't there, you would stop going in a circle and end up going tangentially. Okay, so that means there has to be at least 4,000 newtons keeping you inside centripetally. So what force is keeping you in though? There's no rope tied to the car. So that force actually is the force of friction working on the tires sideways as it's going. Okay, the force of friction of rubber on dry road. Okay, so if our force of friction has to be at least 4,000 newtons, we can find out what the coefficient of the road is, because force of friction is mu Fn. Okay, and Fn on a flat ground, we know that this, we'll assume that this is flat ground, is mu Fg. We know Fg is mass times acceleration, so it's mu mass 500 times 9.81 is 4,000. And you can solve for mu. Divide by 500, divide by 9.81, and we end up with mu is 0.8155. So if this were to be true, coefficient of friction of the ground would have to be 0.82 or greater. Alright, last one was a bonus. This one was a tricky one. Overall, if you look at this, you're going to have some sort of kind of sea to sky thing, where in reality it goes 2.5 meters out, and then a rope hangs 2.5 meters out there, and it says that it hangs 20 degrees from the horizontal like that. So that we're saying this is 2.5 and this is 2.5. Okay. So generally any of our circles that we've dealt with is just horizontal. It doesn't have these two components. Okay. So we know problems that if it hangs straight from the middle point, and that's where the person's holding it from, then you know how to do it. Okay. Okay, but this case is going out and then down like that. So the theta there is 20 degrees. So this is kind of your circle here. Okay, and then it comes out from the middle, and then the person's hanging from the thing. So if it's spinning kind of around a circular point like this, it's similar to if the thing was higher and it was spinning from way up here. Okay, you can picture it 20 degrees hanging from that middle point going down. It would be similar to hanging from this point 2.5 meters out like that. Okay, so our end goal is to find out what FC of this would be, and then it would also hang down at FG. Okay, and that's what gives us our angle. It's the difference of the FC and the FG. Okay, so FC we know is mv squared over r. Okay, but they want to know what the speed is, so we won't know what that will be. Okay, but we know that 20 degrees is going to be O over A, or the inverse of tan. Okay, so we know that tan 20 has to be O FG over FC. So overall, we know that FC is going to be FG over tan 20. Okay, so let's put in our variables. FC is mv squared over r. FG is mass times 9.81 over tan 20. Implies, we're going to divide by the m, so those will cancel out. And let's solve for our v. Our v is going to be the square root of 9.81 m, not m, sorry. We're going to times by this r, so it's going to be r all over tan 20. The hard part is what's r? So if we look at our picture, it's not going to be 2.5 plus the 2.5 here, kind of. It has to be what it would be from here all the way down to here. Okay, so it's going to be your 2.5 plus whatever the hypotenuse here is going to be. Okay, the hypotenuse from here to here turns out that it's going to be this part right here. Turns out it's just a triangle. It's a right triangle here with this 2.5. It turns out it's going to be x over cos 20. Okay, so your r overall is going to be this part, x over cos 20, plus the remaining part down here, 2.5, because that's how long the rope would have been, 2.5. And sorry, I wrote x, but I meant 2.5. So it's 2.5 cos 20, which is this hypotenuse, plus 2.5 is our overall radius in the end. So if I take this, r, and plug it in for there, then I can find out what my speed is. Okay, so my speed is 9.81 times this r divided by tan 20, take the square root of it, and we get v equals 11.62 meters per second. That was a tough bonus question. Thank you.